Okay, this is the Calorimetry Lab, and I'm not sure which one it is, but it will look like this document, and it will have these pages. Of course, you'll want to read it and set it up in your lab notebook so that you have all the information you need to write the report in your notebook, and you'll create tables in your notebook so that you'll have a place for information to go. And your tables will be very simple. One will be for the calorimeter constant, and you'll need this information: mass of the hot water, mass of the cold water, temperature of the hot water, temperature of the cold water, and the final temperature. That's for the calorimeter constant. Then you'll have 3 other experiments that you'll perform after the calorimeter constant. You must have the calorimeter constant before you proceed. This is an acid-base reaction, which does generate some heat, and you'll have an initial temperature, you'll have a final temperature, you'll have a total mass of the water that's in the calorimeter, and I'll show you how to calculate that. And from that, you will be able to calculate the enthalpy of the acid-base reaction based on the amount of water produced in the reaction. Then you'll have heats of solution. The enthalpy of solution for sodium carbonate, the enthalpy of solution for sodium hydrogen carbonate. One will be exothermic, the other will be endothermic. And you'll need an initial temperature of the water, final temperature, and then the mass of both the sodium carbonate added and the mass of the water. Similarly, for the sodium hydrogen carbonate, initial temperature, final temperature, mass of the sodium hydrogen carbonate, and mass of the water. All right, so we're going to fill those tables in as we proceed. First, we have to get the calorimeter constant. And to do that, all we need is first to construct the calorimeter. And the calorimeter is a very simple device. It's an insulated system. We have 2 styrofoam cups with a lid and a thermometer. I used to have a stirring device in there, but it complicated things just too much. We're going to use the thermometer to stir. One other thing we need: something to hold the calorimeter to keep it from tipping over. That would work. Let's see if this one works better. Yeah, this one works better. Okay, this is just to hold the calorimeter because styrofoam is so light and glass is heavy, it would tip over, and we don't want that. Okay, so that's our calorimeter. Now, once you've constructed your calorimeter, you cannot change anything about it. You cannot use a different thermometer, you cannot use different cups or lids, because we're going to determine the constant that's applicable to that calorimeter and none other. So, first thing we need to do, we need to get hot water. Let's see if this water is hot enough. It needs to be at least 70 degrees. And this is distilled water. And it looks like it's made it to 70. Okay. That's good. Now, the key to using a calorimeter is that you know the temperatures right before the reaction takes place, which means you'll have some of the reactant or water, whichever the case may be, in the calorimeter, and you'll know that temperature. And anything else you add to it that you need to know the temperature of, you'll get the temperature immediately before you combine them. So here's what we're going to do. We're going to use another styrofoam cup to hold the hot water. We'll put the room temperature water, which we call cold water in this experiment, in the calorimeter. And the method says we need 75 milliliters of room temperature distilled water. So we'll put 75 milliliters, and this needs to be very accurate, as close as you can get it. All right, so I'm going to use this in order to, and remember, you read the bottom of the meniscus, the curve of the liquid. A little more. There we go. 75 milliliters of room temperature water goes in the calorimeter. Now this is the initial temperature of the cold water. And we stir it around. And then the hot water is going to go in this styrofoam cup. We're going to measure it in here, but this is at room temperature. So when we add that hot water to this, actually it would be better to use this. The water won't cool down as much in plastic as it will in glass. So we'll use this one to measure the hot water, 75 milliliters, same as the cold water. And then we're going to take that 75 milliliters and pour it in here. And then we'll measure the temperature in the styrofoam cup, not in the graduated cylinder. We want to know the temperature of the hot water immediately before we combine them. Okay? So, and this thermometer must stay with the calorimeter. This is an integral part of the calorimeter. You cannot change it. So that's why we need a second thermometer to measure the hot water. All right, so I'm going to need something, a pair of gloves. I know where I've got a pair in here, something I can hold it with. Let's see, I believe it's over here. And, well, I'm looking in the wrong place, I guess. Nope. One last place. Here we go. All right, my hot hands. These are my hot hands. You guessed it, for grabbing hot stuff. So this one's going to be a little more difficult to pour to the right mark, and I'm going to use, let's see, here. I'm going to use a transfer pipette to get the last little bit in there, because I want this to be accurate. All right, so I need my hot hands. Maybe I can do it with one hand. I'll just support with the other one. All right, so I need 75 milliliters. Now, I bet I went over. So let's see. Oh, it's very, very close. We'll just take a little bit out. Just a touch. There. Exactly, 75. Now we're going to put this in the styrofoam cup. And since timing is so critical, you're going to have your lab note. Well, you would have your lab notebook here, right here, to write the numbers down. So your partner would write if that were the case. But in this case, I'm going to write these down and then put them on the board. So, what's the cold water temperature? Temperature, cold, equals what? Get it up eye level, and it looks like 21 degrees. 21 degrees for the cold. Centigrade. And temperature initial for the hot equals what? All right. Let's stir this around and get a good temperature on it. You know, sticking a thermometer in here absorbs some of the heat. So the temperature of the water goes down, but it will tell us the heat right before the temperature, immediately before we combine them. Okay, still creeping up a little bit. Nope, that's it. 6123.5. 63.5. And the final temperature, the final temperature is the same for both of them because they're combined, they're in the device. So we open up the lid and we pour the water in and stir. And we also watch because we want the maximum temperature that's obtained. It's still going up. It's at 39, up to 40, still going up. Crept just above 40, 40.5. As soon as it starts to go down, that's as high as it's going, 40.5. So 40.5 degrees C. Notice that the cold temperature and the hot temperature were about 40 degrees apart, and now their combined temperature, since they were equal masses, 75 and 75, the combined temperature is in the middle. But it's not exactly in the middle. Why is that? That's because some of the heat that was added with the hot water was used to heat up the thermometer and to heat up the rest of the calorimeter. And that's the heat we want to account for. So let's put this on the board. This information. What's the mass of the hot water? 75 milliliters of water is 75 grams. 75 milliliters of cold water is 75 grams. Temperature of the cold water, 21 and 0 degrees. 21.0. Oh, I got that turned around. Excuse me. That's the hot water. 63.5 degrees. See? And this is 21.0 degrees. See? And then the final temperature is 40.5 degrees centigrade. Okay. We have all the information we need to calculate the calorimeter constant. We're going to go ahead and finish the experiment, and we'll come back and do the calculations afterwards. Now that we have that data, we can actually do the experiments using this calorimeter. So what do we do next? We be sure that we keep this thermometer with the calorimeter, and this one is separate. There. Okay, we need to empty the calorimeter. This is distilled water. Go down the drain. And we're going to leave it open like that so it comes to room temperature before we start the rest of the experiments. Okay. Now, what's next? Part 1 in your experiments is the enthalpy of neutralization. That just means how much heat is evolved, and this is an exothermic reaction, how much heat is evolved in the process of neutralizing an acid with a base. All right? So our acid is going to be sulfuric acid. We're going to use 60 milliliters of 0.5 molar sulfuric acid and put that in the calorimeter, 60 milliliters. Then we're going to measure out 50 milliliters of sodium hydroxide. 1 molar sodium hydroxide. Okay? So, here's our sulfuric acid, and I better glove up for this. We just using water earlier. That's no big deal. But now we're using acids and bases, and we need better gloves. Can't pull too hard on these things. Now they'll just come apart. Let's try this one. All right. So here's their sulfuric acid, 0.5 molar, and we need 60 milliliters of that. All right. So here we go. 60 milliliters of sulfuric acid, 0.5 molar. There's 50. Okay, I think I went over. So I'm going to use my pipette. This has only had water in it. And I'm going to remove enough to bring us down to 60. And remember, when you read these things, there's a line going all the way around. If you see 2 lines, you're not level. If you only see 1 line, your eyeballs are level. So we'll just take a little bit out of it to bring it down to 60. Here we go. And this is safe enough to rinse down the drain. That's had acid in it, so I'm going to keep it with the acid bottle. And this goes in the calorimeter. All right, let's rinse that out. So we can use it again for the base. That's the acid. Now, notice that the acid is 0.5 molar. It's 1/2 molar. But the base is 1 molar. So we're using similar volumes, but they're different concentrations. Why is that? Well, sulfuric acid produces 2 protons for every molecule, whereas sodium hydroxide produces only 1 hydroxyl. per molecule. So it takes 2 sodium hydroxide molecules to neutralize the 1 sulfuric acid. So that means that if the sulfuric acid is only half molar, then the sodium hydroxide needs to be 1 molar, needs to be twice as concentrated, so that when we match the volumes, they equally neutralize. But did we match the volumes exactly? No. We put 60 milliliters of sulfuric acid in here, and we're going to put 50 milliliters of 1 molar, well, not sodium hydroxide, pardon me, potassium hydroxide. That's one of the changes in the method. The method calls for sodium hydroxide. We're using potassium hydroxide. Works the same, exactly the same. But why do we use 50 milliliters of potassium hydroxide and 60 milliliters of sulfuric acid? It's simple. Experimental error. If you want the reaction to be complete, you need to have an excess of one of the reactants so that the limiting reactant is completely used up. So we're going to make potassium hydroxide, our limiting reagent, at 50 milliliters, and we make our excess sulfuric acid at 60 milliliters. So when you add them together, there's plenty of acid to completely neutralize the potassium hydroxide, and we get a complete reaction. Now, what does that do for our calculations? Well, we need to know the total mass of the water in here. And we're assuming that the specific heat of this solution is that of water. And the concentrations are so low that that's an accurate representation for the specific heat of this reaction mixture. So, what's the total mass of water in the container, in the calorimeter? It's 60 grams, 60 milliliters of sulfuric acid, 60 grams, and 50 potassium hydroxide. So 60 plus 50 is 110 grams is the total mass in the calorimeter. So now let's make up the potassium hydroxide. And we need to be measuring the temperature here. I'm not going to fasten that real tight because I want to be able to remove it quickly. We're going to get the initial temperature, and the initial temperature for both of them should be equal. We'll find that out in just a minute. But we need 50 milliliters of potassium hydroxide. So let's measure 50. See how close I can get. Get rid of the bubbles so I can actually read the liquid. All right, I got just a hair too much. So let's get a fresh transfer pipette and remove just a little bit of the potassium hydroxide. So it'll come down to the mark. There we go. All right. Keep that with the potassium hydroxide. Now, if the initial temperature of both potassium hydroxide and sulfuric acid are identical, that makes our calculations so much easier. So let's use the other thermometer to measure the temperature. And this is the initial temperature for both, we hope. All right, so let's see what the temperature is for the acid. Let me hold it up to eye level. I got 21.5. And for the potassium hydroxide, Exactly, 21.5. Very good. 21.5 degrees is initial. Temperature initial for both, 21.5 degrees centigrade. So when we add them together, we should see a rise in the temperature. Ready? We don't want to take any of that potassium hydroxide with us because we just measured it out. Let's clean this off. There we go. Now we're ready to add them together. Close up our calorimeter and start measuring, watching the temperature change. It's on the rise. 25. 26. 26.5. Creeping up just a hair. Make that last uncertain digit. Oh, still going. 27. Made it to 27. Let's see, is it starting to come back down? Yep. So it maxed out at 27 degrees centigrade, 27.0, because that last uncertain digit is an estimate. Okay, so let's put this information on the board in our table, which we have prepared beforehand. The total mass, remember we said it was 110 grams, 50 grams of 50 milliliters, 50 grams of potassium hydroxide, and 60 milliliters, or 60 grams, of sulfuric acid. Total is 110 grams. So the initial temperature was both, for them both, was 21.5 degrees C, and the final was 27.0 degrees centigrade. Okay? That's experiment number 1. Now we're going to go to the heat of solution for sodium carbonate. Okay. So, what do we need for that one? Well, we need to start fresh. We need to rinse this off because there's excess acid. Remember? We put excess acid in there so that the reaction would be complete. So we clean our calorimeter. Make sure there's nothing left behind. Don't want to lose that lid because that is part of our calorimeter. And okay. Now temporarily we'll just set that there. And let's see, did we rinse this out? I think we better rinse it again just to be safe. Get rid of all the potassium hydroxide. Okay. Now, acid base is done. That goes over there, that goes with that. Sodium carbonate. All right. So how are we going to do this? Well, we need an initial volume, or mass actually, of water and a mass of our sodium carbonate. And the method calls for 75 milliliters of water. So we'll take room temperature water, 75 milliliters, and put it in the calorimeter, and that will be our solvent. see. Here we go. Coming up on 75. A little bit more. There we go. 75 milliliters of water in the calorimeter at room temperature. Okay. So now we need the lid and we need the thermometer. I think this is the right one. It was laying here. Yes, that's the right one. Should have marked them. Okay, now we need how much of sodium carbonate? 10 grams. Okay, we need to know exactly how much. It can be less than or greater than 10 grams, but we need to know the exact number. All right, so first thing you do, of course, is zero the balance with your container in it so that anything we add we know is the reagent. Okay, I'm going to use my spoonula, and we need 10 grams. 10 grams here. All right. It's going to bounce around because of air currents. We'll get the final weight with the lid closed afterwards. Okay. Another one should be just under. All right. Now we're coming up. Notice how I hold my spatula, almost like chopsticks. Very close. Okay, I went over. That's all right. Close the lid and determine the exact weight. 10.144. 10.144 grams of sodium carbonate. Sodium carbonate, 10.144 grams. What's the mass of the water? The mass of the water is 75.0 grams, because water is 1 gram per milliliter. 75 milliliters is 75 grams. Now we need temperatures. What's the initial temperature? Let's take our sodium carbonate and the bottle here and get an initial temperature. All right, we're going to use these. Initial temperature. Let's see what it is. It looks like it's exactly 21 degrees. 21.0 degrees, see? Now the final temperature is going to arrive once we've added the sodium carbonate and the heat of reaction either generates heat or absorbs heat. And we'll soon find out which way it is, exothermic or endothermic. All right. Now let's mix it up real good. Get it dissolved. Temperature's still on its way up. See where we're at. We're up to 23. Yeah, we're up to 22. 23.3. We want to get the peak. What's the highest temperature that's reached? 24. There must still be some sodium carbonate in there that hasn't dissolved yet. The temperature keeps going up. Oh, 24. Still stuck on 24. We'll see what happens when it starts to go down. How high did it go? 24. Looks like it's stuck on 24. Yep, that's as high as it's going. 24 degrees centigrade. So 21 is low, 24 is the high. 21, 24. Where's my chalk? '21 was the initial temperature. 24. So that's definitely an exothermic reaction. Now we'll do a similar procedure for sodium hydrogen carbonate. All right, what's called for first is the cleanup. And let's clean off any splatter. Okay, and then sodium carbonate is harmless at these concentrations. Okay, so now we have ready for the next step. Enthalpy of solution for sodium bicarbonate, which is sodium hydrogen carbonate. Same thing, baking soda. This one calls for 75 milliliters of water also. Right? So we'll put 75 milliliters of water in this one, as we did before. Let's see. Now let's bring it up to 75 with our wash bottle. There we go. 75 milliliters of water. There. And we'll rebuild our calorimeter. This will be our initial temperature again. Now, while we're waiting, let's see. That's been used. We'll clean it later. This is our sodium. That's our sodium carbonate. That's sodium carbonate. I need sodium bicarbonate. It's always good to double check. Aha! Here it is. Baking soda, which is sodium carbonate. Okay, so let's go measure out how much. 7 grams. So we'll get close to 7 grams as we can after we set the 0 and clean our spatula. All right, so I need there. Okay, we're zeroed. We're going at or near 7 grams. Very close. Coming up on it. Whoops, went past. There we go. Let's close the lid and get a final mass. Seven 7.019. 7.019. Seven 0.019 grams. And the mass of the water, exactly the same as in the previous experiment. Grams, that's a 0. Now all we need is temperatures. And we'll have all the data we need to determine the various heats of the processes. Okay, let's see. Stick this back in its bag. Sodium bicarbonate. All right, initial temperature. Let's see what the initial temperature is. .5. 20.5. Let's see. 20.5 degrees is the initial temperature, and the final temperature we'll determine after adding the sodium bicarbonate. Here we go. As it goes into solution, what's happening to the temperature? Oh, it's dropping. What does that mean? That means we have an endothermic reaction, a heat of solution that's endothermic. Still going down. We're down almost to 17. Hitting 17 right there. Let's see, does it go any deeper? Appears to be stopped on 17. Let's see. Let's see what's going to happen. Yep, I think we reached bottom. Yep, a little bit lower. Let's give it another whirl. It's below 17. We're going to have to estimate that last one. Looks like 16.8. All right. 16.8 degrees C. So let's put that on the board. Then we can talk about calculations. Initial temperature, 20.5 degrees C and 16.8 degrees C. Final temperature. Okay, that's everything we need. Alrighty. Now, let's do a little cleanup before we get into calculations. Put our thermometers away. And let's see, this needs to be rinsed out, I believe. No, we just have water in there. That's still good. And we need to tear down our calorimeter. Okay. So let's rinse it out. Here we go. Rinse off the lid. There we go. Now, let's rinse this out. And this one hasn't been rinsed out yet. And retrieve my spatula. All right. So let's talk about calculations. Okay. That's enough cleanup for now. The calorimeter constant, in fact, the method, the document that you'll follow, it's in Blackboard, and at the bottom of this first sheet is a sample calculation to determine the calorimeter constant. So let's talk about that. What does that mean? Well, the system that we're using is defined as an isolated system. You can have three types of systems when you're talking about heat transfer, right? This is your system, and this is the surroundings. Okay? Now, if heat that we use for a little Q is going into the system, it's relative to the system means it's a positive value. If heat is leaving the system, Q then will be a negative value. So exothermic values are always negative, endothermic values are always positive. But there are several things that you can do with this setup. One is it can be completely open, right? An open system means that both heat and mass can cross the boundary. Sometimes that's useful, but for our purposes, it's rarely useful. Then there's the closed system. The closed system is one which does not allow mass to transfer, only heat. All right? And you'll see this type of system in automobile engines, where the heat transfer is essential for the operation of the engine. What we're using with our calorimeter is an isolated system. Okay? An isolated system. That means that heat does not cross the boundaries. So you're probably asking yourself, well, if you do that, then where's the endothermic and the exothermic? Well, the endothermic and the exothermic are in the system. So the temperature of the system will increase for an exothermic and decrease for an endothermic reaction. So our system is isolated. So what does that mean for our calculations? All right, What that means is that everything that happens in Vegas stays in Vegas. Everything that happens in the calorimeter must sum up to 0. So any heats that are being transferred are transferred within the system, and they all cancel out to 0. Right. So for the calorimeter, the heat of the hot water plus the heat that's contained in the cold water have to equal 0. So one would be equal in magnitude to the other, but opposite sign. Except that the calorimeter contributes something itself. So we have to add in what happens to the calorimeter in this process. And that calorimeter is always there for every experiment that we conduct. Okay? So here's how you do it. Well, what does the Q for water mean? Well, the Q means that you have a specific heat for water, which is 4.184 joules per gram K. K is Kelvin. It's the same size degree as centigrade. So we could just as easily write degree centigrade here. All right? So it's this value times the mass of the water, in this case, times the change in temperature. And the change in temperature, let me tilt my head back. The change in temperature is always the final temperature minus the initial temperature. So if the final temperature is lower than the initial temperature, like it was for this one, is that right? Let's see. Yeah, the final temperature is lower for that one. Then subtracting a larger temperature will give you a negative value. Okay. So this is what represents Q for hot, and the same thing for cold, because we're talking about water and it has the same specific heat. It just may have a different mass and have a different change in temperature. But the calorimeter is slightly different than that. We can't write this, and that for the calorimeter because we don't know what the specific heat of the calorimeter is. So what we do is we combine these two terms, and they're equal to a big C. That's the calorimeter constant. And that's why once you build your calorimeter, you cannot change it. Because if you change it, you change the mass and maybe even the specific heat of one of the components. So once you determine this constant, it's good only for that calorimeter. Right? So now it's C, calorimeter constant, times delta T. Now what are the units of measure here? Well, this is degrees C, or K. This is grams. And this is these units. So these degrees cancel, these mass cancel, and you're left with joules, right? So the unit of measure for this term is joules. Same here, joules. How about this one? This is degrees C, or K, and the calorimeter constant is joules per degree C, or K. So the degrees C cancel, leaves you with joules. Okay? And all of these have to add up to 0. So we know the mass, we know the change in temperature, we know the specific heat for the hot water, the cold water, and we know the change in temperature for the calorimeter because it's the same as the cold water. We put the cold water in there first, so its initial temperature is the same, its final temperature is the same. and that will give us a delta T here equal to the one here, and then all we have to do is solve for C. All right? So I'm going to set it up, but I'm not going to solve it for you. So let's set it up. This needs to be C, calorimeter constant, times delta T. This is going to be similar to that one. So we got this value, that we have the mass of the hot water, which is 75 grams. And we have initial temperature of the hot water is 63.5. Oops, we want final. Excuse me. Final first. The final temperature for the hot water and the cold water are exactly the same because they equilibrated together in the calorimeter. 40.5 minus 63.5. Okay, that's this term right here. Now the second term for the cold water. It's the same specific heat, same mass, and then the final temperature is the same, 40.5, minus the initial temperature, 21. Then our last term, right? So this is that term, this is this term. Let's see, this is that term, this is that term, and this is unknown times delta T for cold water because the calorimeter and the cold water were together initially. So this one is 40.5 minus 21.0 degrees C. Okay? So there's the problem set up. All you have to do, since it's all equal to 0, you got one unknown. Just combine these terms, combine those terms, and then solve for C. All right? So I gave you as much as I'm going to give you on that one. How do we do the others? All right. So this is for the calorimeter constant. And it's on video, so I can erase it now and move on to the others. Okay. We still have to be equal to 0 because our system is isolated. But in an acid-base reaction, what we've got is only two terms, actually. We have the heat of neutralization and the heat of the calorimeter. So the heat of neutralization is going to be calculated like this. You have the S for water, which is 4.184 joules per gram. Let's use degree C. Well, actually, no. We don't need that yet. My mistake. Let's see. This is Q for the reaction. Not G, Q. For neutralization. How much heat for neutralization? No. Hold everything. Okay. Now I got it. I left out a term. We've got a Q for the water that's being absorbed. And we also have a Q for the reaction, the acid-base reaction. So we do have three terms. Right? This is an unknown. We don't know that one yet. But we do know the heat that's being transferred in the water. Right? So this will be 4.184 times the mass, 110 grams, and then the change in temperature, final minus initial, 27 minus 21.5. Right? Then we need to introduce the calorimeter. You're going to have a value for this constant that came from that calculation. So you're going to put that value in here. And then the change in temperature is the same as for the water. All right? So you're going to put a value in there. Then you're going to come up with a value here for the heat of the reaction. And this is going to be in joules. Okay? That's so many joules for this neutralization reaction. All right? So how do you express that in terms of heat for the reaction? Well, it all goes back to neutralization. So if you have an acid like this one, sulfuric acid, plus the base, you always get water and a salt. Oops, my mistake. I'm still thinking sodium. It's potassium. All right. So to balance that, we need let's see, 2 of these. I need 2 of these. There we go. And that will give us 2 of those. 4 hydrogens, 4 hydrogens, sulfate, sulfate, 2 potassiums. We're balanced. Okay, so you're going to have so much heat as part of the reaction. How do you express that? Well, we express it in terms of the moles of water produced. Right? So how many moles of water were produced in this reaction? We had 60 grams of sulfuric acid, and we had 50 grams of KOH. Okay? So, notice that the moles of potassium hydroxide equals the moles of water. So if we know how many moles of potassium hydroxide were produced, then we know how many moles of water were produced. And for acid-base reactions, we express the results in terms of moles of water because every reaction produces water, every acid-base reaction. So we need moles of potassium hydroxide. So how do you get that? How many moles of potassium hydroxide were actually added? 50 milliliters, which is how many liters? 0.050 liters. What was the concentration of KOH? 1 molar. 1 molar times 50 liters gives us the number of moles of KOH equals 0.050 moles of water. Okay, so now we know how many moles of water because they're 2 to 2, 1-to-1 ratio. So however many of this you have, you got the same amount of water. Now, express the Q of reaction here, which is in joules, divided by the moles of water. and that gives you a value of heat per mole of water produced, and that you will compare to the accepted value, which is at the back of your, here we go. So there's the accepted value of 57. Actually, that should come out a negative number since it's exothermic. So this is the number of kilojoules per mole for acid-base reaction. Okay? So that's what you compare it to. This is going to be joules per mole. That value is kilojoules. So you need to match your units. How do you convert one to the other? You should already know that. All right. So this is the acid-base reaction. All right. Now we need to do, I'm just going to do one of these because the other one is calculated exactly the same way, except that it's going to be relative to the number of moles of this, the number of moles of that. All right. And those accepted values are also here in this document. Sodium carbonate value, sodium hydrogen carbonate value, which is endothermic, and sodium carbonate is exothermic. So you need to find out how many moles of this were in the reaction, right? Here. You need the molar mass of sodium carbonate to convert that to moles. You need the molar mass of sodium hydrogen carbonate to convert that to moles. And then once you find the heat for the reactions, you can ratio them just like we did here. Okay. So the calculation is similar to that for acid-base reaction. We have this, it's set up like instead of, well, the heat of reaction or the heat of solution. Right? So this is going to be your unknown. And the heat of the water for sodium carbonate is 75 grams of water, 4.184 specific heat, 75 grams, and final temperature, 24 minus 21. 24 minus 21 initial temperature. There. And then you have the calorimeter, big C, that you have to plug in because you determined it earlier, times the same temperature change. Okay? Then once you get that value in there and solve for this unknown, you get a heat value. And you need the number of moles of this, convert that to moles. All right? And then you have the heat, and you get a value there that you can compare to the unknown. Do the same thing for this one, only don't forget, it's final minus initial. So this one is going to be final minus that one makes it negative on this side of the equation. But when you take that value and put it over here, it becomes positive. So that's why the sodium hydrogen carbonate equal to this one is positive, and the sodium carbonate started positive here, becomes negative on this side, makes it exothermic. All right? You may have to pause this video several times, particularly for the parts where I made a mistake, and then go back and review the different parts, because the calculations are not that difficult if you're methodical and use 0 equals everything else that happens, because the system is isolated. You need to calculate the calorimeter constant because it has to go into every calculation for the following 3 experiments. Right? So I'm going to leave that up to you. And all I'm going to do now is just take another look at the document. There is a No, there's not. There are laboratory questions. All right? Laboratory questions. Calculate the enthalpy of neutralization from your calorimeter data in part 1. You've done that, but it asks you questions. Is your value the same as the true value? What's the true value? Well, it's not the true value. It's the accepted value, which is in this table. Is neutralization an endothermic or exothermic process? How do you know? Exothermics are negative values. Endothermic are positive values. Then you do the same thing for the sodium carbonate and for the sodium bicarbonate. Basically the same questions, 3 questions. Then there's a calculation on the back that might give you fits. I don't deny that one. So let me see if I can give you a hint. All right, the first one, commercial hot and cold packs are based on chemical and physical changes, right? Everybody who's worked in a hospital setting or in a clinic knows that you have these watery packs with a little solid thing bouncing around inside, and in order to activate them, you break that capsule inside, and that starts the solution. Well, one is similar to, it's not exactly like this, but one like this would make a hot pack, and one like this would make a cold pack. So the question is here, design your hot pack using sodium carbonate. Okay, so we are going to use sodium carbonate for the hot pack. If the desired temperature of the hot pack is 50 degrees centigrade, how many grams of sodium carbonate must be dissolved in a pack that contains 500 milliliters of water at room temperature, 20 degrees? All right, so this is basically working backwards. We worked forwards to find the heat of solution. But now we're going to use the accepted value for the heat of solution, the heat for the sodium carbonate from your table. And that value is, here it is, minus 23.30 kilojoules per mole. All right. So we're going to assume that we have an isolated system in that bag. And the bag then says that everything that happens has to add up to 0. So we're going to have a, that's wrong. Again, this is the delta H of reaction for sodium carbonate. So we're going to have a Q for the reaction, right? We're going to have a Q for the water that's in the bag, and we're going to assume that the calorimeter, or the bag itself, right? We can calculate this one, 4.184 joules per gram degree C. And how many grams are in that bag of water? 500 grams. And what's the change in temperature? What's the delta T? Well, the initial temperature is 20, right? 20 degrees. And the final is 50. So 50 degrees minus 20 degrees C. Okay? So that's what's happening to the water. So this Q for the reaction is equal to 0. Solve for Q. You get a value for Q, right? Once you resolve this one, then it comes over on this side with a change sign, and you have a Q for the reaction, which is in joules, right? So that's the amount of heat that you have to account for. So this many joules corresponds to how many moles of sodium carbonate? Well, it's a dimensional analysis problem. If you have this value and you need to cancel the joules, actually kilojoules, then let's see. You want to divide this by kilojoules, by the Q of the reaction. Q of the reaction divided by 1,000, right? Because you start with joules and you want kilojoules here. Actually, it should be the other way around, because you want moles of sodium carbonate. So if we put Q on the top, divided by 1,000, then this is joules, this is kilojoules, they cancel, and then the moles comes out on top, and this equals to moles of sodium carbonate. Okay, now you know the moles of sodium carbonate, you can find out the grams. You just convert it with molar mass. And we do the same thing for the other problem, which is for sodium bicarbonate. We want to make a cold pack that goes from 20 degrees down to 1 degree. And the mass is the same for water, 500 grams, and you get a Q for that one. And in that case, you use a different value for the heat of reaction, which is from the table. Excuse me, yeah, that's negative, is positive. Right, so 17.15 positive, since it's endothermic, is for kilojoules per mole, and that's sodium bicarbonate. So you do a similar calculation, and you convert the moles eventually to grams. All right, so that's all the hint I'm going to give you. Besides, I've made so many mistakes at this point, you don't want me to help you anymore. You want to do it on your own and get it right. Okay, so let's see. I'm going to take another scan with my head camera. And this changed along the way, but these are the raw data numbers. Raw data numbers for each of the experiments. Okay, that's it.